Again, welcome to calculus class. In this lecture, we will go through functions. So again, this is our unit 1, lecture number 6. Again, we are still on pre-calculus subjects. So here again, we're going to learn how to again evaluate a function, also state the domain of a function, and also find the decomposition of a function, and also find the composition of a function. So first, we start with the definition of a function. Here we are going to explain the meaning of a function, the domain of a function, and also the range. So here we say let D and R be two sets of real numbers. Again, D and R will be a two sets of real numbers. Then a function f is a rule that matches each number x in D with exactly one number y or f at x in R. And D is called the domain of the function, and R is called the range of a function. So here we can see that the main definition saying if we have X number in a domain, it should match only with exactly one number of Y in the range. Let's assume that X is our input and Y is our output. So that means an input variable should only give us one answer for output, not two answers. Then it's a function. So again, a function f is a rule that matches each number x in a domain with exactly one number y in a range. So in a function, there's only one y value or f at x value for each value of x. So let's see an example here how to again evaluate a function. So here we have a function f at x equal to x squared. We are going to evaluate f at 3. So since the function is x squared and we have 3 as the variable, anywhere we see x, we are going to substitute with 3. So we're going to have 3 squared. So we have x squared, so it's 3 squared. So our answer will be 9. And this is read as f at 3. And again, 3 is substitute for x. Now, next is f at 5. So again, the same concept. Anywhere we see x, we are going to substitute with 5. And again, our function is x squared. So we are going to have 5 squared, which will give us again 25. Another example for C, we are looking for f at -2. So this means anywhere I see s, I'm going to substitute with -2. So in this case, I'll get -2 squared, which again will give us 4. We have a new function here, f at s equal to x cubed minus 2x squared plus 3x plus 100. And here we want to evaluate f at 2. So it's the same concept as our previous example. Anywhere we see x, we are going to substitute with 2. Then we solve the function. So we will get 2 cubed minus 2 squared plus 3 times 2. Again, x cubed will be 2 to the power 3 minus 2 times x squared will be 2 times 2 to the power 2 plus 3x will be 3 times 2 plus 100. So we have 2 cubed minus 2 times 2 squared plus 3 times 2 plus 100. And that will give us 8 minus 8 plus 6 and 100. So our answer will be 106. Now let's try f at a. So the same thing, anywhere we see x, we are going to substitute with a. So we get a cubed minus 2 times a squared plus 3 times a plus 100. We are using the same function. So we substitute x with a because we are looking for f at a. So since we don't have any like term, the answer will be as it is. Also, we have f at a plus 1. So anywhere we see x, we are going to substitute with a plus 1. So s cubed will be a plus 1 cubed minus a plus 1 square plus 3 times a plus 1 plus 100. So here we can expand our cube, which will give us a cube plus 3a squared plus 3a plus 1 minus 2. This is perfect square, so to give us a squared plus 2a plus 1, then 3 times a and 3 times 1 plus 100. So we're going to combine the like terms. We have a square, another a square, so that will give us 1a square. So a cube plus a square. Then we have plus 3a minus 4a will give us minus 1a plus 3a will give us plus 2a. So we have plus 2a. Then we have a constant value 1. 1 minus 2 will give me minus 1. Minus 1 plus 3 will give me plus 2. Then plus 100 will give me 102. So next we have f at a plus 1. So this means anywhere we see s, we are going to substitute with a. And at the end, we are going to add 1 to the function. So we can see there's a difference between f at a plus 1. F at a plus 1, everything is in the parentheses. So anywhere we see x, we are going to replace it with a plus 1. By here, we have f at a. For the parentheses, is only a plus 1, addition 1, which means we substitute all the x with a, then we add 1 to the function. So we can see we have a cubed minus 2a squared plus 3a plus 100. Anyway, we see x tend to a. Then we add 1 to it plus 1. So the like term is the constant value. So our final answer will be a cubed minus 2a squared plus 3a plus 101. So there's a caution here, as we said earlier, f at a plus 1 in the parentheses is not the same as f at a plus 1. Because f at a plus 1 parenthesis means anywhere we see x, we substitute with a plus 1. By f at a, then plus 1 means anywhere we see s, we substitute with only a. Then at the end, we are going to add 1 to the function. So the answers are not the same. Another example, we have f at s equal to s squared minus 8s. And here they say we should evaluate f at 5 minus f at 2. So what we're going to do is, first of all, we are going to find f at 5. So anywhere I see x, I'm going to substitute with 5 and get the answer. Then I'll look for f at 2 also. Anywhere I see x, I'm going to substitute with 2 and get the answer. Then I'll find the difference of f at 5 and minus f at 2. So that's what we're going to do now. So f at 5 will be 5 squared minus 8 times 5. And that gives us 15, negative 15. Then we look for f at 2, which will be 2 squared minus 8 times 2. And that will give us 4 minus 16. And the final answer will be minus 12. Now we find the difference of the two, f at 5 minus f at 2. And that will give us minus 15 minus 12. And that will be minus 15 plus 12. And that will give us minus 3. Now let's do another example, f at s plus h. So anywhere we see our x, we substitute with s plus h. Substitute s plus h for x. So here we have again s squared plus 8x. So it will be s plus h squared minus 8 times s plus h. We can open the parentheses, perfect square, which will give us s squared plus 2sh plus h squared. Then we open the parentheses for the second, minus 8 times s will be minus 8x, minus 8 times h will be minus 8h. Then we see if we can combine some like terms. Here we cannot combine, so we leave the answer as it is. Next, we're going to find f at s plus h minus f at x. We already know f at s plus h, which is our previous answer, so that's it here. We substitute again. Then f at s will be the same equation, so it's s squared minus 8x. F at s is s squared minus 8x. F at s plus h, anywhere I see s, I'm going to substitute with s plus h squared, s plus h. So here we can again remove the parentheses. Here will give me minus x squared plus 8x. So we combine the like term, s squared will cancel minus x squared, and minus 8x will cancel plus 8x. And I think that's it. So we get 2sh plus h squared minus 8h. And that will be our final solution. Now, this is a piecewise function. A piecewise function means the function is discontinuous somewhere. So we may have two or more equations or functions with different intervals. So here we have a real estate broker charges a commission of 6% on sales value up to $300,000. Now, for sales value at more than 300,000, the commission will be 6,000 plus 4% of the sale price. So now they say we should represent this condition of commission, how the real estate broker will earn. We should represent this as a function R. So we know that 6% is 0.06, so it will be 0.06 times X, only if the value is up to 300,000. So we can say from 0 to 300,000. Then the next one, we have a commission of 6,000 fares plus 4%, which will be plus 0.04 times the sales. Let's say X again. Only if S is greater than 300,000. So we can see our solution is 0.06x, which means the sales start from 0 all the way to 300,000. Now, greater than 300,000, we get 6,000 face money, so that's 6,000. Then we get 4% of the commission. The sale price is S, so the 4% will be 0.04x. This means if X is greater than 300,000, that is if the house is sold more than 300,000. So this will be our piecewise function. We have two expressions, but with different conditions, especially the interval. Now we have the piecewise function. They say we should find R 200,000. That will fall in the first piecewise function. So we get 0.06 times 200,000 because the equation there is 0.06x. S is the sales price, 200,000. So that gives us 12,000. Now we're also going to find R 500,000. So 500,000 is greater than 300,000. So we need to use the second function, which is again 0.04 times X, in this case, 500,000, plus the 6,000, which is here. So later we get 20,000, then 500,000 times 0.04 will give me 20,000. So I'll get 20,000 plus 6,000. And that's 26,000. Now, next question says we should find the domain of the following function. So f at s equal to 1 divided by s minus 2. So anytime we have a ration, the denominator value always shouldn't be 0. It can be any value, but it shouldn't be 0. So this means our domain will be any value of s except 2, positive 2. Because if s is positive 2, I'm going to get, again, 0. Any value divided by 0 is undefined. There's no solution. So we said that since the denominator can be 0, that is s minus 2 not equal to 0. That is the domain consists of real numbers, but only 2. 2 will make it 0. So we can indicate that s can be any value except 2. So s not equal to 2. Another example, we stay finding the domain. But here we have square root of s minus 2. Remember we said the domain, we should be able to get an answer. And anytime we have a square root of a negative value, we cannot get the y value because this is a real number. So this is also the same concept. If s is greater than 2 is good. But if s is less than 2, we have problem. So the solution here will say, since we are only interested in real numbers, s minus 2 must be non-negative. So the domain is indicated by s minus 2 should be greater than or equal to 0, or x should be greater than or equal to 2. If s is 2, it's okay, because 2 minus 2 is 0, square root of 0 is 0. But if it's less than 2, we are going to get a negative value, which is not good. So also we can use the vertical line test to test if a function or an expression or algebraic expression is a function. So here we say if any vertical line intersects a graph at more than one point, then the graph is not a function, or the graph does not represent a function. So this is an example. This is a function. We can say the vertical line again touches the function only once. So that's our vertical line. So this is a function. The vertical line touches the function only once at any point on the function. Then second, we have a circle. We can see that a circle, at some point, it may again touch twice. A vertical line will touch twice. So this is not a function. So this is our solution. The graph shows that the equation does not represent a function because the vertical line can be drawn that intersects the graph in more than one point. So that, again, that will be the conclusion of our lectures. Again, these lectures, we start with the function, and we're trying to understand the basic concept of a function. So here we have the definition of a function. Also, we talk about the domain of a function and how to evaluate a function. Now, in next lectures, we will go through how to find the decomposition of a function and also the composition of a function. So again, wish everybody the best, and thank you.